is just some extra practice problems for you. Again, I have these for every chapter we're going to cover. This does not negate you guys practicing stuff on Chem 101 or in your textbook or anywhere else. So please find other resources to practice, but here's just some more examples kind of worked out. They're worked out at the end of your student notes. The PowerPoint slides from here on are at the end of the PowerPoints I give you, so you have access to it there as well. And you can see the worked out examples either through the video, or if you want to check, or if you don't want to watch video, just check quickly. These are again posted at the end of the student notes, so please check that out. The whole point of these videos is just to walk through these examples with you slowly, so that sometimes just hearing someone explain it makes a little more sense on why we do a certain conversion or why we perform a certain operation than just looking at someone else's work. I hope this helps. So, chapter 1, focusing on matter, measurements, and problem solving. Lots of significant figures, lots of dimensional analysis, lots of conversions. So that's what this is going to focus on. So the first examples we have here, these are examples 1 through 5 in your notes. And so I forgot to put the numbers in here, I apologize. 1, 2, 3, 4, and 5. So we're going to work them in this order. The first example, we've got 4.932 multiplying by 39.47, and then that quantity is, we're subtracting 3.21 from that quantity. So when you're looking at this example, you need to realize orders of operation. So back to, I don't remember what math class we learned these in, but whenever you learned orders of operation, PEMDAS, if you remember that. That's how I was taught it, at least. If you plug this directly into your calculator as written, it will follow the orders of operation because your calculator is going to do multiplication first, then subtraction. But if you don't plug things into your calculators properly, calculators don't care about orders of operation. They're going to just do what they want. In this case, though, we can plug this directly in because the hierarchy is that this is going to happen first, then this quantity, we're going to subtract 3.21 from that quantity. If you're confused at what I mean with orders of operation, please come see me in office hours. Okay, so 4.932 has 4 sig figs. 39.47 also has 4 sig figs. When I multiply these two together, I get a calculated answer of 194.6604. And I know I want 4 sig figs. I'm not going to round yet. I'm not going to round until the end because I don't want to create round off error in my measurements. I am, however, going to mark where that sig fig should sit. It should be, in this case, 4 sig figs would be my tens place. From this quantity, I'm going to subtract 3.21. And this calculated answer will be 191.45604. Now, remember, multiplication and division, we look at the number of sig figs. But for addition and subtraction, we look at the decimal place. So now we need to look at our decimal places. Here, I'm at the tens place. Here, I'm at the hundredths place. We need to limit our sig figs to the least precise measurement, which will be the tens place. So we need to round our number to here. So our final number here will be rounded to 191.5. If you have 5 or higher for the number you're getting rid of, the first number to the right of the number you're going to end up keeping, you're going to round up. So we round this up to 191.5. Okay, next example, 5.982 times 0.00201. This has 4 sig figs. This has 3 sig figs. Remember, leading zeros, not significant. Captive zeros, zeros stuck between 2 other digits, are significant. When I multiply this together, I get the value 0.01202,382. For multiplication division, we need to keep the least number of sig figs. So I'm going to count 1, 2, 3. Those leading zeros are not significant, but this zero I underlined is in fact significant. The final answer here will be 0.0120. That answer does have 3 sig figs. That 0 is after a decimal place, after an integer. The other way to check yourself is you can always put this into scientific notation, and that number is still in fact significant. What about this example? 4.953 plus 9.20 divided by 11.315. By orders of operation, if I plug this into my calculator, it's going to give me the wrong answer. Orders of operation, because I'm using the division sign like this, it acts as a parenthesis. It's really telling me to do this math, the numerator's math, before I do the division from the denominator. So I'm going to take 4.953 and add that to 9.20. That's going to give me a calculated answer of 14.153. Remember, for addition and subtraction, we're looking at the least precise value. So here we go to the third decimal place, here the second. So our final answer will be accurate here to the second decimal place. But I'm not going to round yet. I don't want to create round off error. So I'm going to take this whole value and divide it by 11.315. But you need to recognize here that this has 4 sig figs, while this has 5. Which means my final answer can only have 4 sig figs. So when I put this in my calculator, I get 1.250817,499. Again, calculators don't care about sig figs. You need to count to the 4th sig fig, 1, 2, 3, 4. I need to cut my number right here. Now, up here, forgot to specify, when I cut it here, there was a 2 after, so I just rounded down, which is why I kept the 0. Here, I need to round up because I'm getting rid of an 8. This equals 1.251. So, first calculation, second calculation, you can do either one of these answers here. They're the same answer. Third calculation. We do have some more examples like this throughout because, bottom line, students just struggle with these examples, and that's completely fine. But you need to have these down because when we're doing it applied to chemistry, it just gets a little bit more difficult. We obtained 5.68 grams of a compound for an experiment. A few minutes later, you obtained an additional 8.32 grams of the same compound. What is the total mass of the substance? Well, let's see. We've got 5.68 grams. A little bit later, we get another 8.32 grams, which means I'm going to add these two values together. You can either write these on top of each other so it's really easy to see where your decimal places are, or you can realize that each value has 2 decimal places, so our final answer needs to have 2 decimal places. If I put this into my calculator, it's going to give me an answer of 14. Although that's not correct, it's not precise either. I need to say 14.00, and I need to put the unit on there. If you get a number with a unit, you need to include the unit. There's very few times in chemistry that we do not include units. There's some very specific cases, and we will make that very clear to you when units are not included. Often, 97% of the time, you must have your units included, or the answer is not correct. Okay, number 5. 8.672 times 10 to the 6th divided by 1.376 times 10 to the 4th. Because I'm doing division here, I need to look at the number of sig figs. So I have 4 sig figs in my numerator and 4 sig figs in my denominator. That makes the math easy. I don't have to do much. I don't have to think about it much. I just need to keep 4 sig figs in my final answer. When I calculate this out, I'm going to get 6.30232558. And that is times 10 to the negative 10th. It's a pretty small number, but I'm dividing a small number by a fairly big number, so I expect it to get pretty small. I want to keep to 4 decimal places. 1, 2, 3, 4. So I'm going to cut it right here. I need to cut between that 2 and 3. Because it's a 3, I'm going to round down, and I'm going to say 6.302 times 10 to the minus 10. Don't forget this at the end. Students will forget that because the number seems so long and they forget it's at the end. Don't forget that. This is not 6.302. It is 6.302 times 10 to the negative 10th. Very different numbers. If you're going to tell me that you're going to give me, $6.302, okay, $6, that's cool, whatever. I can get something small, but if you're going to tell me you're going to give me 6.302 times 10 negative 10th dollars, I don't know how small you're cutting that penny, but it's pretty dang small. Okay, so we're on to 6, 7, 8, and 9. Example 6. We have 5.74 centimeters plus 0.823 centimeters plus 2.651 centimeters. Now, you are more than welcome to write these out vertically to each other. What I mean by that is you are more than welcome to rearrange this and say 5.4 centimeters, 0.823 centimeters, and 2.651 centimeters so that you guys can quickly figure out where to draw the line. And then add it up from there. I'm completely fine with that. I don't like taking the time to do that. I am much faster, so whichever one's faster for you, do it. I am much faster at just counting my decimal places and saying, okay, 2 decimals, 3 decimals, 3 decimals, and that's how I do the math. I want you to pick what's most comfortable for you. When I add this up, though, I get a calculated answer of 9.214. I know that my least precise value is 5.74. It is to the second decimal place, meaning I need to keep this to the second decimal. So I'm going to write 9.21. But I'm not done because I have these units. They're all in centimeters, which means I can add them up. But I need to make sure to write centimeters here. Number 7, 4.8 liters plus 3.965 liters. When I add this up, I'm going to get 8.765 liters. I have 1 decimal place. I have 3 decimal places. I'm going to keep my answer to 1 decimal place. I'm going to round this to 8.8 liters. Number 8. Now I'm doing multiplication. 5.02 nanometers times 89,665 nanometers times 0.1 nanometer. These are all length units. A nanometer is a unit of length. But if you recognize this, we're going to get nanometers cubed here, which can correlate to, eventually we could do a conversion. We're not going to in this example, but we could do a conversion back to centimeters cubed and then to volume. To 1 centimeter cubed equals 1 milliliter. This is how we find volume. It's your length times your width times your height. So back to geometry. That's what this is looking at, is actually calculating a volume of something. You need to be aware of that because you have to pay attention to what you're doing with units here. So let's go back a little bit. Let's look at our sig figs here. When we look at sig figs, we've got 3 sig figs here, 5 sig figs here, and 2 sig figs here. Remember, leading zeros are not significant, but trailing zeros, after a decimal, after an integer, are in fact significant. So our final answer here needs to have 2 sig figs. When I plug this in my calculator, I'm going to get 45,011.83. I need to keep this to 2 sig figs though. So I'm going to round to here. I'm going to say 45,000. But I've got a nanometer times a nanometer times a nanometer. That is the same as nanometers cubed. So nanometer times nanometer gives me nanometers cubed. Number 9, 5.892 divided by 6.10, and I've got grams and milliliters here. First, let's do the math. I've got 4 sig figs here and 3 sig figs here. Again, trailing zeros are significant. We're going to keep them. They're going to be happy if we keep them around. So our final answer must have 3 sig figs. Calculate this out, and you're going to get 0.9659016 393. I need to keep this to 3 sig figs, so I'm going to round to here. I'm going to cut the value here. Because the 9 is the first number I'm going to get rid of, I'm going to have to round up. So my final answer here is going to be 0.966, but I'm not done. I need to put my units in. I've got grams per mil. Those are, in fact, my units. I am taking grams divided by milliliters. It's completely valid units, too. That's actually the units we use to represent density. Okay. Number 10, 11, 12, and 13. So let's look at 10 first. We've got 2.526 divided by 3.1 plus 0.470 divided by 0.623 plus 80.705 divided by 0.4326. By orders of operation, we're going to do each individual division piece first, and then we're going to add all the numbers together. So here I've got 4 sig figs, here I've got 2. When I do this math, the 2.526 divided by 3.1, my answer is 0.81483879097. It's pretty long. Do you really need to write all that? No, you're not going to create round off error that far up. I'm going to keep a few numbers after, but I'm going to round it to about here. Because my significance is only to that second decimal there, only 2 sig figs. I'm keeping 3 numbers past that. I am not creating round off error at that point. 0.470, 3 sig figs. 0.623, 3 sig figs. So my final answer here needs to have 3 sig figs. When I do this division, I get 0.754414. And at 3 sig figs, I would round to this 4 if I was going to round right now. 80.705 has 5 sig figs, and 43.26 has 4 sig figs. When I divide 80.705 by 0.4326, I get 188.1273. I need to keep 4 sig figs, so I'm going to go to the value here, the number 1. Now I'm on to addition. So now I need to look at how precise is my measurements, and I need to round to the least precise measurement. This is the 100ths place. This is the thousands place. This is the tens. I'm going to round my final answer to the tens. I apologize, I wrote the wrong number right here. I wrote the number for the overall summation here. This should be 1.865580. It is still to the tens place here. I just wrote the wrong number and I apologize for that. When you add this all together, you should get the answer 188.12727. But I know I need to keep this to my tens place because this is the least precise. Which means my final answer here will be 188.1. .404 times 2.91 divided by 18.7 minus 17.1. The division sign here acts as a parentheses. So I'm going to take 6.404, multiply that by 2.91 first. I do that and I get a value of 18.63564. That's a calculated answer. Here I actually have 4 sig figs. Here I have 3 sig figs. So if I was going to round, if this is my final answer, I would round to the 3rd sig fig here. I'm going to divide this value, however, I'm not going to stop yet. I'm going to divide this value by the quantity found from 18.7 minus 17.1. The answer here is 1.6. Note, this has one decimal, this has one decimal, this has one decimal. That answer is correct. 1.6 is correct there. There's no rounding error there. That's just literally the only answer. After that, I would put zeros. So that is the actual answer here. If I needed more significance, I would write a 0 after that 6. But I don't. Now I'm going to divide 18.63564 by 1.6. I get a calculated answer of 11.647275. I need to round this based on sig figs. So I've already identified where my sig figs are here. This has 3 sig figs. This has 2 sig figs. I need my final answer to round to 2 sig figs. So I'm going to cut my answer here. I need to round that answer up to a value of 12. So I can keep just 2 sig figs. Number 12. I have 9.5 centimeters plus 4.1 centimeters plus 2.8 centimeters plus 3.175 centimeters divided by 4. This is doing an average. I've got 4 measurements here and I'm doing some kind of average. When I look here, since I'm doing the division line here, again, acts as a parenthesis. I need to do the addition first. I have 1 decimal place, 1 decimal place, 1 decimal place, and 3 decimal places. When I do the addition, I need to keep my final answer to 1 decimal place. So when I add up 9.5 plus 4.1 plus 2.8 plus 3.175, I get a calculated answer of 19.575. If I'm to look at how many decimal places I need, again, I'm going to keep it to 1 for the decimal place here. But this is going to be divided by 4. Now the 4 here, you could argue either way. You could argue that this answer is an exact number or a measurement. I'm going to tell you it's an exact number. I'm going to tell you that you made 4 measurements, and therefore, what that means is that 4 does not limit your final sig figs for the answer. Instead, it's just a value. It's like how 100 centimeters equals 1 meter. It doesn't limit our final answer. If I take 19.575, divide that by 4, I get a calculated answer of 4.89375. And now I need to round this. This does not limit sig figs. This has 3 sig figs. I need to round my final answer to 4.89, which contains just 3 sig figs. Okay, 9.875 times 10 to the second minus 9.975 times 10 to the second divided by 9.875 times 10 to the second kilograms. I forgot to fix this in here. I apologize. This does say percentage in your notes. This is how we find a percent error. We take a known value and subtract out some other value. What we normally do is an absolute value here, just so that we can have a positive number, because we don't really, sometimes we care which way the error leans, if it's a positive error or negative error, and right now, it doesn't matter because the bigger number comes first, but you'll see that when you take lab second semester. Anyway, let's go ahead and look at this example. 9.875 times 10 to the second kilograms minus 9.975 times 10 to the second kilograms. We are doing subtraction, and we're doing this with scientific notation. So when I calculate that out, it's going to give me an answer of 8.0. So my numerator is going to be 8.0 kilograms, and that's going to be, 8. I apologize for that. The 8.0 is what's important in a sec, and then divided by the 9.875 times 10 to the second kilograms. But we have to look at our significance, our precision in our measurements, because we're doing subtraction. So remember the shortcut for doing scientific notation. You want to see basically what value are you at. This is 10 to the second, which means 10 to the first, 10 to the 0, 10 to the negative 1, or the first decimal place. 10 to the second, first, 0, and negative 1, or first decimal place, which is why this answer would actually be 8.0, not just 8. So make sure you guys are paying attention to that when you're doing scientific notation. So there is 2 sig figs here, and there's 4 sig figs down here. Now for our division step. So we will be limiting our final answer to just 2 sig figs. We do this calculation here, and then we multiply this by 100%. The 100% is an exact measurement. We're just taking something from a fractional form into a percentage, so it does not limit our sig figs. Overall, you should find your answer here with correct sig figs to be 0.81, and do not forget to write that percent symbol, because percent is your unit in this case. Okay, numbers 14, 15, and 16. Convert 1.76 picometers to centimeters. Remember, when you're doing dimensional analysis, to first write down, what do you want to know? We want to know centimeters. So I'm going to say number of centimeters. Second thing you're going to write down is what measurement you're given. You're told 1.76 picometers. Pico is lowercase p. If you know the conversions between the individual units, so pico to centi, that's fine. I always teach my students to do it through the base unit. So we're always going to convert through meters or liters or grams when I'm doing an example. Again, if you want to do it the other way, that's just one direct shot, that's fine. But if it goes awry and you get it wrong, I'm sorry. So I'm going to convert through meters first. I'm going to convert to meters, and I know it takes 10 to the 9th picometers to equal 1 meter. At this step, I've canceled out my picometers and I have meters. Now I'm going to use my conversion to go from meters to centimeters. I know there are 100 centimeters in 1 meter. That cancels out my meters and I have centimeters, which is what I want. When you calculate this out, you're going to find the answer to be 1.76 times 10 to the negative 7 centimeters. Now, you can do these conversions as long as you've got them written correctly. I do not mind. So I use 1 meter to 10 to the 9th picometers. You could also write 10 to the negative 9th meters to 1 picometer. Those are both correct. I said 100 centimeters to 1 meter. You could say 10 to the 2nd centimeters to 1 meter. You could say 1 centimeter to 10 to the negative 2nd meters. All of those are correct. They're all going to give you the same answer. If you're unsure about that or uncomfortable with that, pause this video and work them all out using a different conversion. You will get the same answer every time. I don't care which one you use. I flip around whatever one my brain picks out of the ether at that moment in time. So more often than not, I'll do whole numbers like this because I like bigger numbers. But whatever works better for your brain is what I want you guys to use. I'm not insistent upon using one conversion over the other as long as you're doing your conversions correctly. Okay, convert 43 degrees C to Kelvin. Remember, Kelvin is equal to degrees C plus 273.15. You need to have that memorized. There's no ifs, ands, or buts about it. We're going to be using Kelvin for the entire school year. So you need to be comfortable with Kelvin. So this is equal to 43 degrees C plus 273.15 equals 316.15 K. If I look at this now, I'm doing addition. This is to the 10 to the 0 space, or the ones place. meaning no decimal places. So I'm going to round this to 316 Kelvin. And the boiling point of liquid nitrogen is negative 196 degrees C. What is the temperature on the Kelvin scale? Again, Kelvin equal to degrees C plus 273.15. So I have negative 196 degrees C plus 273.15. And when you add this up, you're going to find that your value is 77K. So we've got to round to the first place here. You're going to have to round up. When you do this calculation, you should get a 76.85. You're going to round up to 77 because we need to keep it with no decimal places because our least precise measurement is negative 196. Okay, number 17. A European car is advertised as having a gas mileage of 15 kilometers per liter. Convert this rating to miles per gallon. We have some conversions that we're provided with here. We've got 1 meter, lowercase m, means meter, means a few other things too, but it means meter, equals 1.094 yards. 1,760 yards equals 1 mile. We use MI to abbreviate miles. 1.06 quarts is equal to 1 liter, and 4 quarts equals 1 gallon. So first, write down what do you want to know? Well, you want to know miles per gallon. Next, write down what you're told. You're told 15 kilometers per liter. Then use conversions to get to where you want to go. So I see I have a conversion for a meter to a yard. Now, you can convert the numerator first or the denominator. I don't care if you do distance first or volume first. I tend to convert whatever's in the numerator first and then work on the denominator. Do what's comfortable to you. Okay? So we're going to work on converting kilometers over to miles, and then I'm going to work on converting liters to gallons. So 15 kilometers, I do have a conversion that has 1 meter equal to 1.094 yards. I know a conversion between meters and kilometers. So I'm going to do the conversion I know to convert to meters, then I'm going to use the conversion that's provided to convert to yards. So I know there's 1,000 meters in 1 kilometer. If I was to stop right here, my kilometers have canceled out and I am in meters. Now I can use this conversion. So times 1.094 yards per 1 meter. How do I know what goes in the numerator and what goes in the denominator? Because I'm trying to cancel things out. So I'm trying to cancel out my meters, and the only way to cancel my meters is to put it in the denominator. Plus, I'm eventually going to need my distance in the numerator, so it makes sense that way too. But if you think about what's canceling, sometimes that can help get you on the right track. Now I am in yards. What can I do now? Well, I have a conversion for yards going to miles. And overall, I want to get to miles, so that's the perfect conversion to use. I know 1 mile is equal to 1,760 yards. How do I know it's 1 mile? Because it says 1,760 yard equals mile. That implies 1 mile. That cancels out my yards and leaves me with miles. So now I've got my numerator set. Now I just need to work on my denominator. So let's work on our denominator. We've got liters, we want gallons. Well, I have a conversion here showing me a quart to a liter. So I'm going to go ahead and use that conversion. I'm going to say 1 liter in my numerator and 1.06 quarts in my denominator. Why am I doing it that direction? Because I need to cancel out my liters, and my liters are currently in my denominator. Now I'm in miles per quart. I want miles per gallon though, and I've got a conversion for quarts to gallons. Times 4 quart to 1 gallon. And if I stop here, that cancels out my quarts and leaves me with gallons. Now I've got all of my units correct. When I calculate this out, I'm going to have it in miles per gallon, which is exactly what I want. When you calculate this through the calculator, you're going to get an answer of 35.18439. And again, I know I've mentioned this in class, but it does not matter. You can do all the numerator, then all the denominator. You can mix it up. I don't care. What do I mean by that? In your calculator, you can say 15 times 1,000 times 1.094 times 4 divided by 1760 divided by 1.06. You could say 15 times 1,000 times 1.094 divided by 1760 divided by 1.06 times 4. Those will give you the same answer. That's because multiplication and division have equal weight in orders of operation. Do what you're comfortable with. But when you calculate this out, you are going to get an answer of 35.18439. We have to think about our sig figs really quick. This is an exact measurement, which means it does not limit our sig figs. This has 3 sig figs. This has 3 sig figs. This has 4 sig figs. This is exact. How do I know that? If you are in the metric system, they're exact. So this is within the metric system. It's exact. For 1 quart to 4 gallons, I just know that one. There'll be times that I will tell you guys if they're exact. And if I'd given you this on like a quiz or something, I would say exact next to it. All I would say is the word exact next to the conversion. You need to know what exact means, but I don't always expect you to know that. The only one that I can think of off the top of my head that I know you have to know is 2.54 centimeters equals 1 inch. That's exact. You need to know that one. But back to it, we've got 2 sig figs here. Our final answer needs to be limited to 2 sig figs. So I need to round this to 2 sig figs. I'm going to say 35 miles per gallon. So 15 kilometers per liter, 35 miles per gallon. Pretty good gas mileage. Okay, number 18. The density of pure silver is 10.5 grams per centimeter cubed at 20 degrees C. If 5.25 grams of pure silver pellets are added to a graduated cylinder that contains 11.2 milliliters of water, to what volume level will the water in the cylinder rise? So this is called a displacement method, and it's often used in laboratories to figure out the volume of an irregularly shaped item or species. So you've got a graduated cylinder here. And you've got some volume in it. And graduated cylinders are just that. They're graduated. They have lines on them telling us different volumes. Let's say our volume is actually down here, so it's easier to draw where I'm at. We're going to go and we're going to put into here 5.25 grams of silver pellets. So, because I don't have a color silver on here, let's say I put the 5.25 grams in here, they're down here, and now my volume is here. So my volume's here now. This is the volume. This difference here is due to those pellets. The amount of volume increase here is due to the fact that those pellets were put into that system. So what volume is this water going to be at? It's going to be, the final volume is going to be 11.2 milliliters plus the volume of silver. Well, how do I figure out the volume of silver? I have its mass and I have its density. I'm going to rearrange that to solve for its volume. So density is equal to mass over volume. In this case, our density is equal to 10.5 grams per 1 centimeter cubed. I'm going to rearrange this and use the mass of the actual substance we have, the amount of pellets we have, to figure out the volume of pellets I have. If I want to find volume, I can rearrange this to solve. If I take your mass and divide it by density, it's going to give me volume. So I've got 5.25 grams divided by 10.5 grams divided by centimeter cubed. This gives me 0.500 centimeters cubed. Now I know some students are not comfortable with doing it that way, so let me show you the slightly longer way. This is the same as saying 5.25 times 1 centimeter cubed divided by 10.5 grams. You're saying the same thing here, okay? It's just a conversion. Whichever way you're comfortable writing out, it's going to give you the same answer. But I know that 1 centimeter cubed is equal to 1 milliliter. So I know that 0.500 centimeter cubed, I can write that as times 1 mil divided by 1 centimeter cubed. This equals 0.500 milliliters. Now I can add this volume to this. And I can figure out the total volume of the graduate cylinder once the silver pellets have been added. One more thing, why did I keep this to 0.500? Why did I add 2 zeros here? I added 2 zeros because, I apologize, there's 3 sig figs here, and there's 3 sig figs here. So I need to keep 3 sig figs in my answer. So I've got 11.2 milliliters of water plus 0.500 mils for the space added from the silver pellets. This will give me a calculated value of 11.700 mils. Now I'm doing addition, so I need to think about how many decimal places. 1 decimal, 3 decimals. I'm going to round this and say my final volume is 11.7 milliliters. Number 19. A roll of aluminum foil is made out of a long aluminum sheet that is 304 millimeters wide and 0.016 millimeters thick. What maximum length of aluminum foil can be made if we have a 1.10 kilogram sample of the aluminum? So how are we going to go about solving this? Well, we're given some equations here, cube, sphere, and cylinder. And thinking about this one, if I've got my width and I've got my thickness, I'm going to use cube. I'm going to figure out how long can I make this piece of aluminum foil and compare that back to, so I'm looking at for length here, but I've got my kilograms. I know my width and my thickness. I can use all this information to figure out what length of aluminum foil I can find. So first thing I'm going to do is I'm going to use density to relate mass and volume. If I look up the density of aluminum foil, I find it to be 2.7 grams per mil, which also means grams per centimeter cubed. Note there is 2 sig figs in this measurement. You can find density more accurate. When I looked it up on Google, that's just the first thing that came up, so I'm going to limit all of our answers to 2 sig figs. Not really that big of a deal since we have 2 sig figs here anyway, and it would have been limited to 2 sig figs. When you're doing calculations in the per se real world, if you're doing a calculation and your value you look up, such as density, is what's limiting your values, you should probably find it a little more accurately to a few more sig figs than you have. Because we want your measurement to really limit your final answer, not just whatever constant we happen to look up. Because densities are valid to many more decimal places than just one. So, let's get back to it. I want to know eventually what length of aluminum foil I can get. So, I want to know number of millimeters cubed. I know I have a 1.10 kilogram sample. Well, oh, by the way, why do I want millimeters? Because I'm going to have to use this equation here, and this is in millimeters, and this is in millimeters. So since I'm going to need them in millimeters anyway, I figure why not find millimeters now? I know I'm using a 1.10 kilogram sample of aluminum. I know that there is 1,000 grams of aluminum per 1 kilogram of aluminum. That's just my metric measurements. I know based on density, there is 1 centimeter cubed of aluminum per every 2.7 grams of aluminum. That means if I have exactly 1 milliliter or 1 centimeter cubed of aluminum, it will weigh exactly 2.7 grams. So I know I have more grams than that, but it's going to tell me exactly the volume I have in that case instead. I do want this in millimeters instead of centimeters, so then I'm going to do one last conversion to get this into millimeters. And I know that it's 10 millimeters in every 1 centimeter. Now, be careful when you stop here. This is 1 millimeter over 1 centimeter. 1 centimeter cannot cancel out a centimeter cubed. You need to cube this whole quantity. Now check it and make sure that all of your things are canceling. That should be. Kilograms of aluminum, canceled. Grams of aluminum, canceling with grams of aluminum. Centimeters cubed, centimeters cubed. Everything's canceling, we're going to get millimeters. Be careful when you enter this in your calculator as well. This is the same as 1.10 times 1,000 divided by 2.7 times 10 raised to the third. Granted, you don't have to, you can mix up the order of these things, I don't care about that, but make sure that however you put it in your calculator, this is equivalent to 10 to the third. Most calculators use this little caret sign to say raised to. When you calculate out your number of millimeters cubed, you should find this value to be 407.4074. And this is millimeters cubed. It's a pretty big number, definitely repeating itself. We don't need to keep all of those digits right now, but I'm going to keep them just for the next calculation because I'm going to round at the end. I don't want to deal with rounding error. So now that I know my millimeters cubed, that means I know my volume. I know the volume of aluminum foil, I can make from 1.10 kilograms. Now I want to go ahead and figure out, okay, if I know that, what is the length of the aluminum foil I can use, or I can produce from this? So I've got 407.4074 millimeters cubed. This is equal to length times width times height. Length, which is what I'm trying to solve. Width is 304 millimeters. And height, or thickness, is 0.016 millimeters. Rearrange that equation and solve for length. So length equal to 407.4074 millimeters cubed divided by 304 millimeters times 0.016 millimeters. Note here that this millimeter cancels out with 2 of them up there. And this gives me a final calculated answer of 83759.7 millimeters. It's a pretty big number. I'm going to actually convert that to meters. So, and I'm going to round to 2 sig figs. So, first, that equals 84,000 millimeters, which I'm going to convert. You can write out the conversion if you need to, that's totally fine. but you need to get comfortable with seeing that that would be equal to 84 meters. So if I have a sample of aluminum foil that is 3.04 millimeters wide and 0.016 millimeters thick, the maximum length of aluminum foil that can be made if I have 1.10 kilograms of aluminum foil would be 84 millimeters. 84 meters. Many millimeters, but 84 meters long. Okay. An iceberg has a volume of 7,655 cubic feet. What is the mass of the ice in kilograms composing the iceberg? Hint, the density of ice is 0.917 grams per mil at 0 degrees C. So I want to find the number of kilograms. I have a volume of 7,655 feet. So write down what I want to know, number of kilograms, and write down what I'm given. 7,655 feet cubed, because it's cubic feet. I'm going to go ahead and convert this, because I'm trying to get to kilograms, and I'm going to have to use density here. I know 0.917 grams per 1 mil is the same as 0.917 grams per 1 centimeter cubed. But that means I need to get this value into centimeters. The only conversion I know between the American system and the metric system is 2.54 centimeters equals 1 inch. You may know another conversion, that's fine. That's just the one that I chose to have memorized. So I'm going to go ahead and get my value to inches. So I'm going to multiply this by 12 inches to 1 foot. Make sure to cube that. I need to cancel out those cubes. And I know there's 2.54 centimeters for every 1 inch. Again, cube this quantity. If I see that my feet cubed have canceled and my inches cubed have canceled, and I am now in centimeters cubed. Now that I'm in centimeters cubed, I can go ahead and use my density. So times 0.917 grams per 1 centimeter cubed. Now I'm in grams, and I can easily convert to kilograms. 1 kilogram is equal to 1,000 grams. Again, you could also write that as 1 kilogram is equal to 10 to the third grams, 10 to the minus third kilograms equal to 1 gram. Whatever conversion you know that is correct is completely fine to use. I just tend to use non-scientific notation ones if I can. So, check to make sure. This cancels my centimeters cubed, this cancels my grams, and leaves me with kilograms. Make sure when you plug this in your calculator, you're careful. You've got 7,655 times 12 to the third times 2.54 to the third times 0.917 divided by 1,000. Make sure you're remembering to raise these to the third power, which again is usually that little caret symbol or triangle without the bottom on your calculator. When you calculate this out, you should get a calculated answer, 198,773.9. Now you have to look back at sig figs. This has 4 sig figs. This is exact, which means it does not limit sig figs. This is exact, which means it does not limit sig figs. This has 3 sig figs. So I'm going to go ahead and round this answer to 3 sig figs. So this will equal, you can either write this as 199,000 kilograms, or you'll more often see this as 1.99 times 10 to the 5th kilograms. We'll often put it in a scientific notation when it gets that big, just because it's easy for people to lose zeros when they're looking at them. If we put it in scientific notation, we're not losing those zeros. Okay, lead metal can be extracted from a mineral called galena, which contains 86.6% lead by mass. A particular ore contains 68.5% galena by mass. If lead can be extracted with 92.5% efficiency, what mass of ore is required to make a lead sphere with a 5 centimeter radius? Lots of things going on here. Lots of conversions. You're probably reading this question and thinking, what? It's kind of overwhelming. That's okay. We're going to work our way through it. First, what we need to think about is how are these, just as some background information, how do we often get these materials? We extract them out of ores, out of rocks, out of species in the ground. A lot of the elements, the naturally occurring elements we've been able to extract from other sources. Lead is extracted from this mineral. This mineral is contained within a particular ore. So it's an extraction upon an extraction. And so we can look at these things and we actually can get conversion factors from it. So we know lead metal can be extracted from the mineral, which is 86.6% lead by mass. So that's like, over here we say sterling silver has a silver alloy containing 92.5% silver by mass. We have 92.5 grams of silver per 1 gram of alloy. Here we have 86.6 grams of lead per 100 grams of the galena. A particular ore contains 68.5% galena by mass. That means I have 68.5 grams galena per 100 grams of ore. It's another conversion factor. Lastly, it tells me that lead can be extracted with 92.5% efficiency. That means for every, what that means is I get 92.5 grams galena, 92.5 grams of ore extracted per 100 grams of ore used. So if I have a 100 gram sample of the ore, I'm successfully able to extract 92.5% of that. So 92.5 grams. That other 7.5 grams is just kind of wasted or lost. So how can I go about this? Well, let's see. I want to know how to make a lead sphere. I want a lead sphere with a radius of 5 centimeters. So I know the equation for a sphere. Volume equals 4/3 pi r squared. Pi r cubed. So I know 4/3 pi r cubed, and I want to figure out how much volume do I need? What do I actually need? How much do I need to extract to be able to make this sphere? So I'm going to figure out, well, what's the volume of the lead I actually need? If I can figure out the volume, I can use density to convert back to grams. I can use grams to convert back to how much ore do I actually need, the mass of the ore that I need in the first place. So lots of conversions. It's a very complex problem. So let's look at volume of lead needed. We've got 4/3 pi. R is 5 centimeters. That told us that's what our radius was. Cubed. Calculate this out, and you're going to get 523.599 centimeters cubed. We cubed this entire thing, which means we cubed the 5 and the centimeters. We have 3 sig figs there, so technically our sig figs stop here at 523. I'm just not going to round quite yet. Now that I have my volume, I'm going to use the density of lead to figure out my grams. Sometimes you'd have to look these up outside. Again, on an exam, I would give you the density. But density of lead is equal to 11.29 grams per centimeter cubed. It's pretty heavy. A lot of metals have higher densities. So grams of lead needed. We've got 523.599, marking my sig figs, centimeter cubed, times 11.29 grams per 1 centimeter cubed. This gives me a value of 5911 0.43 grams of lead. So I need about 5,900 grams of lead to make this 5 centimeter radius sphere. Let's figure out how much ore that equates to. How much ore do I actually need in the first place to be able to extract, to be able to pull out that mineral, to be able to pull out the lead? So if I need 5911, my sig figs are under that first one, just to keep them marked for you guys. So we have 3 sig figs here and 4 sig figs here. 5911.43 grams of lead. I know that I can get, or I have 100 grams of galena per the 86.6 grams of lead I can actually pull out. I know that for every 100 grams of ore extracted, I have 68.5 grams of the galena. And I know that for every 100 grams of ore, 92.5 grams of ore is actually extracted. Calculate all this out, and your answer is 10773. And this is grams of ore. Sig figs are still here at 3. Everything their calculations have 3 sig figs. And so I'm going to round this, and I'm going to say 1.08 times 10 to the 4th grams, or you could also, again, write 10800 grams, either one is fine, of ore required. If you want to convert that to kilograms, you can. We don't often report things in kilograms, but you could go ahead and write 10.8 kilograms as well. So I'd have to start with 10.8 kilograms of ore to make that 5 centimeter radius lead sphere. The mass of a fuel in a jet must be calculated before each flight to ensure that the jet is not too heavy to fly. A 747 is fueled with 231 liters of jet fuel. If the density of the fuel is 0.768 grams per centimeter cubed, what is the mass of the fuel in kilograms? So I've got this many liters. I've got your density here. I want to know what's the mass specifically in kilograms. So number of kilograms of fuel, starting out with 231 liters. I know there's 1,000 milliliters per 1 liter. Why am I converting to milliliters? Because I know that 1 mil equals 1 centimeter cubed. So 1 centimeter cubed to 1 milliliter. Now I can go ahead and use density to convert to grams. 0.768 grams per 1 centimeter cubed. And I know 1 kilogram contains 1,000 grams. Calculate this out. You get 133041 as your calculated answer. We need 3 sig figs in our final answer, which is limited by our density. So our final answer will be 1.33 times 10 to the 5th kilograms. I have 1.33 times 10 to the 5th kilograms of fuel. And again, if you feel more comfortable, you should always check, make sure units are canceling. Liters to liters, mils to mils, centimeter cubed, and grams to grams, leaving me kilograms. I recommend making sure units cancel until you guys are very comfortable. And even then, sometimes it's good to check, because sometimes you'll just put things on the wrong side of the equation. You'll put it in the numerator, it should be the denominator, etc. and it can kind of throw off your entire calculation. So you should always check that your units have canceled. Okay, 23. Convert 5.12 times 10 to the negative third grams into micrograms. So I want to know number of micrograms. I'm starting with 5.12 times 10 to the negative third grams. I know micrograms are smaller, so I'm expecting this number to look bigger than it does now. I know there are 10 to the 6th micrograms. This is one of the conversions you need to have memorized per 1 gram. This gives me 5120 micrograms. Or you can write this as 5.12 times 10 to the third micrograms. Do not leave the 0 here if you put it in scientific notation. The way I have this written, this has 3 sig figs. If I had written 5120 with a decimal at the end, that has 4 sig figs. Our final answer needs 3 sig figs. Convert 435 centimeters to kilometers. So number of kilometers is equal 435 centimeters. Again, some of you may know the conversion straight to kilometers. That's totally fine. I always convert through base units because it's the only conversions I personally have memorized. So my base unit is meter. I know 1 meter contains 100 centimeters. Now that I have meters, I can convert to kilometers. I know 1 kilometer has 1,000 meters. This gives me an answer of 4.35 times 10 to the negative third kilometers. Does that answer make sense to me? Yep. Centimeters are much smaller than kilometers, so if I'm converting 2 kilometers, I expect the number to look smaller. And lastly, convert 32.145 times 10 to the 12th nanoliters to a deciliter. I know nanoliters are pretty small. This is a pretty big number here, so I expect the number to get smaller than a deciliter. Deciliter is times 10 to the negative 1. Nanoliter is times 10 to the negative 9 compared to a meter. So I want to know a number of deciliters. I've got 32.145 times 10 to the 12 nanoliters. Again, I'm going to convert through my base unit first. So 1 liter has 10 to the 9th nanoliters. Now that I'm in liters, I can convert to deciliters. I know there's 10 deciliters for every 1 liter. My final answer, 3.2145 times 10 to the 5th deciliters. Okay. Determine the volume of an object that has a mass of 455.6 grams and a density of 19.3 grams per centimeter. These calculations should seem pretty straightforward to you, at least once we're past the first chapter. We're going to use density a lot throughout this entire school year to be able to use as conversion to convert between volume and mass units. So you need to be very comfortable with this concept of density. If I want volume, I've got mass and I've got density. I can reorganize this equation. Density equals mass over volume. If I want to solve for volume, that just means mass over density. So volume is equal to 455.6 grams divided by 19.3 grams per centimeter cubed. This gives me, let's see, where's my answer? 23.6 centimeters cubed. The other way you can do this if you don't like this look here because you can't figure out the units is you can say 455.6 grams times 1 centimeter cubed divided by 19.3 grams. It's doing the exact same thing. It just kind of throws students off. The denominator of your denominator becomes a numerator, but that is hard for students to see sometimes. So if you need to put it into a conversion factor, that's totally fine. Number 27, The density of lead is 11.3 grams per centimeter cubed. What is the mass of lead required to make a 1 centimeter cubed fishing sinker? Well, again, density, mass over volume. I want to know mass, so mass is going to equal density times volume. 11.3 grams per 1 centimeter cubed. Volume is 1 centimeter cubed, so the mass will just be 11.3 grams. So if I want to make a 1 centimeter cubed fishing sinker, I need 11.3 grams of lead. And number 28, can you find the mistakes? I want you to look at numbers 1, 2, and 3 here under number 28 and see, where do you think the mistakes are? Go ahead and pause the video and see what you think. Now, looking back at this, we've got centigrams, and we're trying to find the number of centigrams from the number of micrograms. We have 3,700 micrograms. I don't care if you guys don't write this divided by 1 here. Some students prefer it. It's up to you. It means the same thing whether you put it there or not. 3,700 micrograms, and I'm converting this to grams. I know there is 10 to the 6th micrograms for every 1 gram. So this conversion is correct. It's 1 million micrograms to 1 gram. Then I've got times 1,000 centigrams per 1 gram. This is not correct. This should be 100 centigrams per 1 gram. So that's where the mistake is in the first one. What about the second one? Got 25 seconds. And again, I don't care about these divided by 1 thing here. 25 seconds, and I'm converting this to nanoseconds. I've got 1 times 10 to the negative 9th nanoseconds per 1 second. But a nanosecond is 10 to the negative 9th, right? It is, except the nano is a lot smaller. So it is either 10 to the 9th nanoseconds to every 1 second, or 1 nanosecond to 10 to the negative 9th seconds. So make sure you're paying attention if it is a really big number or a really small number that you're multiplying or dividing by. And the last example, I want number of kilometers per second, and I'm starting with kilometers per hour. I've got 115 kilometers per 1 hour, okay? And I'm going to convert that to seconds. I've got times 1 hour divided by 60 seconds. Not correct. This is where students will mix this up. If you want to do a direct conversion like this, you have to make sure you've got the correct number of seconds there. If I was to do this equation, I would say 115 kilometers per 1 hour times 1 hour per 60 minutes times 1 minute per 60 seconds. Now, this ends up being 3,600 seconds. If you want to do it as one fell swoop, that's fine. I write them out because students often mess up this conversions. Okay? So, look back